Hey everybody, this is Electricity and Magnetism lecture for October 2nd. Um, as you know, I am away, and so we will be doing video lecture today. The topic will be on conductors and capacitors, continuing on that for the rest of the week. And please let me know if you have any complaints about video quality and that sort of thing. I'm jury-rigging this from my hotel room, so we'll see how it works. Anyway, so up until now, we've only been talking about sort of stationary clouds of charge in sort of pure electrostatics. But we want to also have the opportunity to deal with what happens when we have mobile charges around. And as our first gateway to that, we want to talk about the properties of conductors. So what's a conductor and what makes it special and unusual from any ordinary material? Well, all materials are composed of roughly equal amounts of positive and negative charge. But in a conductor, the positive or negative charges are mobile. All right. Typically for something like a metal, copper, aluminum, steel, the negative charges, the electrons are able to move. Whereas for something like salt water, you have both positive and negative ions, sodium and chloride ions, and they're both able to move. All right. It turns out not to matter too much in detail which ones are doing the moving, because when the negative ones they move, they leave positive ones behind, which has the same effect as positives and negatives moving in opposite directions. So a couple of things to say about this. First, for typical metals, the way this works is the majority of the electrons in, say, a copper atom are bonded permanently to the nucleus and can't go anywhere. Um, however, in metals in particular, one or sometimes two or three electrons are not bound to their particular atoms and are free to move around freely throughout the material. You can think of this as metals contain within them kind of an electron liquid that's able to flow around within the interior of the material. They can never leave the material unless you get up to very high electric fields, but are free to move around within it. All right. So conductors have mobile charges. And because typically, for example, for a metal, you have one electron per atom that's free to move, there's a hell of a lot of atoms inside a typical metal, and so you've got a hell of a lot of mobile electrons. What that means is typically for a perfect conductor, there is absolutely no shortage of charge. You will never run out of these electrons. And typically, only a tiny fraction of them are actually involved in the response of a conductor to, say, an electric field. Okay, so how does a conductor respond to an electric field? Well, let me imagine taking a block of metal and suppose it originally started off with an equal number of positive and negative charges, and I subjected it to a externally imposed electric field from the outside world, some charges elsewhere that are making this happen. All right, well, basically what will happen is the positive charges will be pushed by this electric field in the direction of the electric field. The negative charges will be pushed in the opposite direction, such that what happens eventually is you have a situation in which you still have your imposed electric field, but some fraction of the negative charges, oops, sorry, wrong way, have moved over to the left and left behind some fraction of positive charges on the right. Okay. The net effect of this is, remember, electric fields point away from positive charges and towards negative charges. And so within the meat of the material, we have the material itself creates its own induced electric field, which points the opposite direction. All right. In fact, it completely cancels out the imposed electric field, so that the electric field inside is equal to the imposed from the outside world field plus the induced field caused by motion of the conducting charges. And that adds up to 0 inside the conductor, right? As I said, there are so many charges here that they're able to overcome and compensate for pretty much any imposed outside electric field and always render the electric field inside a conductor 0. You might think this is a little magical. How on earth does the conductor know when it's supposed to stop moving the charges around? Well, so long as there's any electric field still inside the conductor, charges will continue to flow in a direction to try to cancel out that field until they're eventually successful in removing it all. All right? So this leads to a bunch of really important consequences and things that make conductors particularly useful. All right. Remember that the electric potential, if we're talking about difference in electric potential between two different points within the conductor. Here's my conductor, here's point A, and here's point B. And we're going to take a path integral from A to B. All right, that gives us the path integral of the electric field is equal to the difference of potential from A to B. All right, I think there's a minus sign here. And, oops, okay, there we go. Path integral of the electric field gives you the difference in potential. All right, and since the electric field is always 0, this is always 0. All right, the consequence of this is the electric potential, the voltage, is always equal to a constant inside a conductor. All right, this is really handy, and you've used this on many, many, many occasions. All right, every time you plug in your iPhone in order to charge it, your laptop or whatever you're plugging it in to charge creates a 5-volt electric potential on one end of the copper wire that your phone is connected to. And you can be sure, because we have a conductor snaking through the cable, the charging cable, that we will also have a 5-volt potential on the other side of the cable. All right. The whole point of electric wires is to take an electric potential from one place and make it available somewhere else. And this only works because the electric potential is always the same inside a conductor. All right, so that's actually super useful. And that's the main purpose that conductors are used for. I should mention that anytime we have a constant electric potential everywhere, we say that the surface or object or whatever is an equipotential. Same potential everywhere on the surface or volume or whatever we're interested in. Another important property of conductors can be identified by remembering the first of Maxwell's equations, which says that the divergence of the electric field is equal to rho over epsilon naught. All right, And since the electric field is always 0 inside a conductor, that means that the charge density is 0 inside a conductor. All right, so the important properties I've identified so far are 0 electric field, constant electric potential, and so far 0 charge inside the conductor. All right, now that doesn't necessarily mean that there are no charges inside the conductor. All right, after all, it's a material, it's made out of positive and negative charges just like everything else. But within the interior, the positive and negative charges always cancel, leaving you with a net charge density inside of 0. All right, does that mean that the conductor itself is overall neutral? Not necessarily. All right, think about what happened in the situation that we were just talking about, where we had a induced electric field. We did eventually have non-zero charges, but they're all located at the surface of the conductor. All right, and so if we have an electric field, say, from the outside world, that's imposed on, say, a circular metal ball, all right, you will have negative charges on one edge, positive charges on the other edge, such that the interior of the ball is equal to 0, and we have a surface charge sigma on one side, and it's positive, and a negative surface charge less than 0. All right. So for a conductor, you can have surface charges, you just can't have volume charges. And that's typically what happens. The conductor rearranges itself, creating surface charges on its surface that cancel out any external magnetic field. Sorry, electric field. All right. Let's see. One final property that I should talk about is that the electric field, I'll just put this here, I guess, is perpendicular to the surface of the conductor. All right. That may seem a little surprising. I just told you that the electric field was 0 inside the conductor. In this case, I mean outside. All right. So if I have a electric field, a conductor here, all right, and I have some sort of electric field lines outside, they must meet the conductor in such a way that the field lines, the direction of the electric field, is always perpendicular at right angles to the surface. All right, this cancellation that I was talking about earlier, that eliminates the electric field, that only works on the inside of the conductor. Outside, there can totally be an electric field, but it is constrained to always be perpendicular to the surface. Why is that? Well, if it were at some angle to the surface, then there would be a net electric field pushing electric charges along the surface. That would push positives in the direction one way along the surface and negatives in the other direction, and they would flow along the surface until they canceled each other. They canceled out the electric field, the component of the electric field parallel to the surface. They can't move off the surface, so there's nothing they can do to cancel out the perpendicular component. So the electric field is always perpendicular to the surface of a conductor. All right, starting up with a new piece of paper, let's consider another topic. Let's talk about cavities. That is to say, holes inside a conductor. All right, well, suppose I have my conductor here, and it's made out of metal or whatever. Oops, sorry, I bumped my camera. And let's suppose we have some sort of, so here's the conductor itself. All right, and let's suppose that I have some sort of hollow area within it. All right, there's an electric field from the outside world that's imposed on this thing. May or may not be straight, doesn't matter. All right, we know that the electric field equals 0 within the meat of the conductor. All right, but what's going on with this cavity? All right, what's the electric field here? Well, we know that along everywhere inside the conductor, we also have a constant electric potential. All right, so we have V equals constant in conductor. And so in particular, V is going to be a constant. We have a constant potential, an equipotential on the inside of the cavity. I guess I should say the inside surface of my cavity. All right, and so we have a situation in which we know that remembering one of Maxwell's equations, the curvature of the electric potential is equal to rho over epsilon naught inside cavity. All right, and so we're left to answer the following question. What function of space, right, V, has no curvature and no second derivatives, or the second derivatives cancel, blah, 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 and has a constant value everywhere on the outside edge of something? All right, well, one possible solution is just to remind yourself. So the basic equation that has to be solved inside the cavity is the Laplacian is equal to the charge density over epsilon naught. The charge density inside my cavity is 0, so that means that the Laplacian, the measure of curvature of the electric potential, is 0. So the electric potential is flat within that area, and we know that it has a constant value on boundaries of the cavity. Can you think of a function that is completely flat and has a constant value everywhere on some outer perimeter? Well, I can. One possibility is that the electric field potential is equal to just a constant inside the cavity. All right, and we will prove later on that the solutions to the electric potential are unique. There's only one possible answer. And so we've been clever enough to guess one possible answer, which is electric potential V is just a constant inside here, and that we will show that that's the only possible solution. If you find one solution, you're done. All right. So we have the electric potential is equal to a constant. So what does that say about the electric field? Well, the electric field is equal to the negative gradient of the electric potential. Electric potential is constant, and so that tells us the electric field is equal to 0 inside the cavity as well. All right, so no matter what kind of crazy electric fields are going on outside the conductor, inside the conductor, all is calm, and there are no electric fields anywhere within it, either in the metal itself or in any hollow cavity contained within the thing. All right, this is the important principle behind the idea of the Faraday cage. All right, which says that you can protect yourself from electric fields by putting yourself inside a metal container. All right. This has got tons of applications, ranging from the mundane and everyday. For example, every computer that you use has a metal or metal-coated outer case. And the purpose of this is to keep electric fields from the outside world from messing up the signals that are going on inside the computer and protecting the computer from harmful electrical interference from the outside world. And it also works the other way around. Electric fields created within the computer can't get out of the Faraday cage, and so they can't mess up the computer next door. All right. It also has some more sort of high-tech and practical sorts of things, sort of high-tech and unusual things. For example, there are folks whose job it is to go and repair high-voltage power lines and to protect themselves as they work on the 100,000 volt electric power lines, which they can't turn off because they're powering entire cities. They just dress up in a big suit of chainmail, and provided you take the proper precautions, such as never touching the ground, the electric fields that are contained and near the power lines can't hurt people inside the chainmail suits. And there are lots of other more practical applications as well. So the classic, example of protecting yourself from, harmful mind control rays from the government by wearing a tinfoil hat comes from the idea that the tinfoil hat will act as a Faraday cage and protect your brain from outside influences. Of course, this is stupid, but it does have some basis in actual physics. All right, so that's the basic idea. Let's consider an example in a little more complicated circumstance. All right, let's suppose we have a sphere with a cavity containing a point charge Q. All right, what is the electric field going to look like when we're inside the cavity, when we're outside the cavity, and when we're outside the cavity but still inside the metal sphere, and when we're completely outside of everything? All right, so here's my metal sphere. All right, it's got a hole in it, and nobody said that hole had to be spherical. All right, so there's my hole. And let's suppose that we have a charge Q inside. All right. Well, we're going to have some electric field from the point charge Q. All right. How is that going to affect the conductor? Well, the conductor is going to have zero electric field everywhere within it. And so if I draw a Gaussian surface that encloses the cavity but remains inside the conductor, all right, we can be sure that the flux of the electric field through that Gaussian surface is equal to 0. And since the electric flux is equal to the charge Q inside over epsilon naught, all right, that means that the total charge inside my dashed Gaussian surface must be 0. All right, and that tells me that there must be a compensating amount of charge on the inside surface of this cavity. All right, so cavity walls have charge minus Q, canceling my charge inside the cavity, which I'm calling plus Q. All right, so the cavity walls have a negative charge that cancels out the positive charge, so that the net influence of the point charge plus the walls of the interior of the cavity have no effect and lead to 0 electric field on the inside. All right, so if the ball started off neutrally charged with a net charge of 0, and by adding this charge inside the cavity, it has, say we put a positive charge inside the cavity, it has attracted a whole bunch of negative charges from the metal that are now piled up on the inside edge of the cavity. Uh, how can that be? Well, they had to have come from somewhere, all right? And so they must have left behind an equal amount of positive charge. And where's that going to be? Well, it can't be in the interior, as I've explained before. It must be on the outside edge, all right? And so the cavity has a bunch of negative charges on the inside, amounting to negative Q, and a bunch of positive charges on the outside, amounting to positive Q, such that overall the conductor has equal amounts of positive and negative charges. All right, and these positive charges on the outside wall, on the outside of the sphere, must be equally spaced, all right? And so, because they're feeling no influence from what's going on inside the cavity, because that's all canceled itself out and there's no electric field to push these positive charges around. So they all try to get as far away from each other as possible. We have a net charge plus Q on outside wall, evenly distributed. So what is the electric field outside the whole big sphere? Well, all right, now the inner cavity doesn't matter anymore. All we have is a spherical shell with a positive charge outside, on the outside edge. All right, and it's pretty easy to use Gauss's law out here. The net charge of all the stuff inside is plus Q. And so it's pretty easy to see that you will get a purely radially outward electric field that is equal to 1 over 4 pi epsilon naught Q over r squared, all right, pointing in the radial outward direction, all right, which is to say the same as a point charge Q. All right, and so this complicated arrangement doesn't matter what shape the cavity inside is. We always have a purely radial charge. It's purely radial electric field pointing out in all directions from our conductive ball. All right, so the conductors are very good at hiding charge and hiding electric fields and making it impossible to see from the outside what's actually going on the inside. They make sure that Gauss's law is still held and the net charge is still whatever the net charge was, but the details of the configuration inside are completely obscured by the presence of the conductor. All right, so that is, I think, all I have to say about conductors. I'm going to stop for 1 second and make sure I didn't miss anything. All right, so at that point, from there I went on and did some more stuff. You can see I got a whole another 2 pages of this stuff. But I've kind of learned through experience that half an hour worth of video lecture usually gets about as much done as I do in a typical class day. And you may be feeling like, you know, you had enough. Anyway, so I'm going to call that quits for today. If you would prefer for me to go the entire 50 minutes every day, please let me know, and I'd be happy to do that, provided I find the time. But I think that's probably enough for today. So on Wednesday, we'll start talking about capacitor work, and I've got a simple calculation for a basic capacitor based on its electric potential and charge and stuff like that. Until then, I'll see you Wednesday. Bye.